In question 1, we've got Sally playing a game in which she can either win or lose. A turn consists of up to 3 games, and on each turn she will play the game up to 3 times. Now, if she wins the first 2 games or if she loses the first 2 games, then she will not be playing the third game. The probability she wins the first game is 0.7. There's the 0.7 on our tree diagram. And if she wins the game, she will win the next one with a probability of 0.6. But if she loses a game, she will win the next one with a probability of 0.2. And we need to complete the tree diagram given here. So we know that the sum of the probabilities on the branches should be 1. So the number here should obviously be 0.3. And then this is 0.6. So this here should be 0.4. So when she loses a game, the probability that she will win the next one is 0.2. So we've got a 0.2 here and a 0.8 here. Again, she lost the first game, so the probability of winning the second is going to be 0.2, and the probability of losing is going to be 0.8. However, if she wins the second game, the probability she will win the third game is 0.6, and this final probability is 0.4. In part B, we want the probability that Sally will win the first 2 games in a turn, so we want the win-win scenario, which is simply 0.7 times 0.6, which gives an answer of 0.42. And in part C, we need to find the probability that Sally will win exactly 2 games in a turn, so we want the win-win scenario. We want the win, lose, and win scenario, that's 2 wins again. And we want the lose, win, win scenario. So we've got a total of 3 different scenarios that give me exactly 2 games being won. So we've got 0.7 times 0.6, that's the win-win scenario, plus the 0.7 times 0.4 times 0.2, that's the win, lose, win scenario, and finally 0.3 times 0.2 times 0.6, which is the lose, win, win scenario, and this gives an answer of 64 over 125. Now, given that Sally wins 2 games in a turn, we need to find the probability that she won the first 2 games. So this is conditional probability. It's conditional on winning the 2 games in a turn, which is the answer we obtained in part C here, the 64 over 125. And we're asking what's the probability that she won the first 2 games. Well, the probability of winning the first 2 games is the 0.42. So the answer to part D will simply be the 0.42 over the 64 over 125. This gives an answer of 105 over 128. And then given that Sally won the first game in a turn, we need to find the probability that she won 2 games. Again, we've got conditional probabilities. Now we know for sure that she won the first game in a turn. So if I go back here, we know that we could be win-win, win-lose-win, or win-lose-lose, because we know for sure that we won the first game. Now, what's the probability that she won 2 games? Well, she's winning 2 games if she's in the win-win scenario or in the win-lose-win scenario here. So my numerator is going to be this probability together with this probability, whereas the denominator will be the sum of these 3 probabilities. So we are looking in the numerator at 0.7 times 0.6, that's the win-win scenario, plus the 0.7 times 0.4 times 0.2, which is the win-lose-win scenario, over the probability of winning the first game, which is 0.7 times 0.6, plus the 0.7 times 0.4 times 0.2, the win-lose-win scenario, plus the 0.7 times 0.4 times 0.8, which is the win-lose-lose scenario, which gives an answer of 17 over 25. In question 2, we've got the weights to the nearest kilogram of a sample of 33 red kangaroos. We are summarizing this in a stem and leaf diagram shown here. We need to find the value of the median and the value of the quartiles. So we are looking for the median. So we know that for the median Q2, we will start by evaluating n over 2. In our case, this is equal to 33 over 2. We've got a total of 33 observations. This is giving me 16.5, and therefore the median Q2 will be given by the 17th observation. So if we look at our stem and leaf diagram, 1 plus 2 plus 3, it's 6, plus 7, it's 13, 14, 15, 16, 17 is 57. So Q2, the median is 57. And we proceed with Q1 and Q3. Well, for the lower quartile Q1, I will be evaluating n over 4, which is 33 over 4. This is giving an answer of 8.25, and once more I round up, so Q1 will be the 9th observation. So once more we go back to the stem and leaf diagram. We've got 6 observations, 7, 8, the 9th observation is a 45, which is the value of Q1. And for Q3, I'll be doing 3n over 4, which is 3 times 33 over 4. This is giving an answer of 24.75, which means that Q3, the upper quartile, is given by the 25th observation. And once more, if I go on my stem and leaf diagram, I will see that the 25th observation is a 63, and therefore Q3 is equal to 63. Now for this data, an outlier is defined to be a value that is greater than Q3 plus 1.5 times the interquartile range, or smaller than Q1 minus 1.5 times the interquartile range. And we need to show that we've got exactly 2 outliers. So I will start by calculating these limits. So I've got Q3 plus 1.5 times Q3 minus Q1, which is equal to 63 plus 1.5 times 63 minus 45. This is giving an answer of 90. And then Q1 minus 1.5 times Q3 minus Q1, which is equal to 45 minus 1.5 times 63 minus 45, which is giving an answer of 18. So anything beyond 90 and anything below 18 will be an outlier. Looking at our stem and leaf diagram, 16 is below 18, 94 is above 90. So all I have to do here is simply state that we've got 16, which is less than 18. We've got 94, which is greater than 90. And therefore, we've got 2 outliers in total within this data set. We're then given the box plot of the same 33 red kangaroos in February, and we are asked to draw the box plot for December. So we will start by drawing the box, which is consisting of Q1, Q2, and Q3 as shown here. And then we need to draw the whiskers. Well, the whiskers are extending up to the last observation, which is not an outlier. Remember, 16 and 94 are outliers, so the whiskers will go up to 23 and up to 86. So that's where the whiskers will stop. And then I will identify the position of the outliers with a cross. So this completes the box plot. We are then asked to compare the distribution of weights in February against December, and we should interpret our comparisons in the context of the question. So first of all, we look at the median. The median in February is obviously less than the median in December. So all I have to say here is that the median in February is less than December. So we know that kangaroos have on average a greater weight in December because the median is simply greater. Then I can look at the spread. I can look at the interquartile range, which is the difference between Q1 and Q3. Well, we see that the interquartile range in February is 16, which is less than the interquartile range in December, which is 18. And based on this, we can conclude that kangaroo weights in December are more spread out. In question 3, we've got Bob, who shops at the market each week. He will buy carrots, that's event C, or onions, that's event O. And we are told the probability he buys carrots is 0.65. The probability he does not buy onions is 0.3. And the probability of buying onions but not carrots is 0.15. We've got the Venn diagram here. W, X, Y, and Z are probabilities, and we need to determine the values of these W, X, Y, and Z. I will start with the last piece of information. The probability we buy onions but not carrots is simply the W here, the only O event. So W is 0.15. I will write this on my Venn diagram, and I will state in my answers that W is equal to 0.15. We then have that the probability that he does not buy onions is 0.3. Well, he doesn't buy onions means we are outside of this, so it's y and z. So we've got that y plus z is equal to 0.3. We also have that the probability he buys carrots is 0.65, which means that x plus y is equal to 0.65. And obviously we know that the sum of all the probabilities, so the 0.15, x, y, and z should be 1. This gives me another equation, so 0.15 plus x plus y plus z is equal to 1. Now what I'll do, I will replace x plus y with 0.65, so we're looking at 0.15 plus 0.65 plus z is equal to 1, which means that 0.8 plus z is equal to 1, and therefore z is equal to 0.2. And then I can easily proceed in finding the remaining unknowns. We had that y plus z is 0.3, so we have that y plus 0.2 is equal to 0.3, which means that y is 0.1, and we also have that x plus y is 0.65, which means that we're looking at x plus y, which is 0.1, is 0.65. So we've got that x is 0.55. This will score all 4 marks, but I will go back to my diagram here to update it with the values for x, y, and z. So x is 0.55, y is 0.1, and z is 0.2. Now for one visit to the market, we need to find the probability that Bob will buy either carrots or onions, but not both. So we want the only onions or the only carrots. So that's going to be simply 0.15 plus 0.1, which gives an answer of 0.25. In part C, we need to show that the events C and O are not independent. Well, we know that events C and O were indeed independent, then we would expect to see the probability of C intersection O being simply the product of the probability of C with the probability of O. Well, the probability of C intersection O is the common region on our Venn diagram. So if we look at the Venn diagram here, it's the 0.55. So I will write this down. Probability of C intersection O is 0.55. And then the probability of C times the probability of O is equal to 0.15 plus 0.55. That's the probability of C times the 0.55 plus the 0.1. That's the probability of O, which gives an answer of 0.455. Now I need to state that the 0.55, the intersection, is not equal to the 0.455, which will justify the conclusion that the two events are not independent as required by the question. In IAI, we've got F, G, and H being 3 events such that F and H are mutually exclusive, F and G are independent. We've got the following probabilities here. I need to find the probability of F union H. Well, the first thing we need to remind ourselves is that F and H being mutually exclusive means that their intersection is empty, so the probability of F intersection H is 0. We also have that the probability of F union H is the probability of F plus the probability of H minus the probability of the intersection. Well, we're trying to find the probability of F union H, which is going to be the 2/7, which is the probability of F, plus 1/4, which is the probability of H minus 0, which gives an answer of 15/28. In part B, we need to find the probability of G, and I will start by stating that since F and G are independent, then the probability of F intersection G is the probability of F times the probability of G. So we've got the probability of F union G being the probability of F plus the probability of G minus the probability of their intersection. Well, the probability of F union G is 5/8. It's been given to us, which is equal to the probability of F of 2/7 plus the probability of G, which I'm trying to find, minus 2/7 times the probability of G. That's the probability of F times the probability of G. Now this is leading to 19/56 being equal to 5/7 times the probability of G. And therefore, if I divide both sides by 5/7, we conclude that the probability of G is equal to 19/40. Finally, in part C, we need to find the probability of F intersection G, where the two events are independent. So the probability of F intersection G is simply the probability of F times the probability of G. We've got both of these probabilities. We're looking at 2 over 7 times 19 over 40. Well, this gives an answer of 19 over 140. In question 4, we've got the probability distribution of the discrete random variable x. This random variable can attain values of 1, 2, 3, or 4 with the corresponding probabilities given in the table here. And we need to show that the expectation of 1 over x is 2 over 5. Now you need to be careful here. The expectation of 1 over x is not 1 over the expectation of x. That would be wrong. What I need to do instead is redraw my table here. We've got x attaining values 1, 2, 3, and 4. So 1 over x could be 1, 1 over 2, 1 over 3, or 1 over 4. The corresponding probabilities remain the same. So it's 1 over 10, it's 1 over 5, it's 3 over 10, and 2 over 5. And therefore the expectation of 1 over x will simply be found by multiplying the 1 over x values times the corresponding probabilities. So we're looking at 1 times 1 over 10 plus a half times 1 over 5 plus 1 over 3 times 3 over 10 plus 1 over 4 times 2 over 5, which is indeed giving me a value of 2 over 5. In part B, we need to find the variance of 1 over x. So let's start by reminding ourselves that the variance of 1 over x is simply the expectation of 1 over x squared minus the square of the expectation. So minus the expectation of 1 over x and all squared. So I will find the expectation of 1 over x squared by simply going back to the table we've just drawn here. Instead of doing 1 over x times the probability, I'll be doing 1 over x squared times the probabilities here. So we're looking at 1 squared times 1 over 10 plus a half squared times 1 over 5 plus a third squared times 3 over 10 plus a quarter squared times the 2 over 5. This is giving an answer of 5 over 24, and therefore the variance of 1 over x, well, we've got the expectation of 1 over x squared, it's 5 over 24. We have just found in part A the expectation of 1 over x, it's 2 over 5, so it's 2 over 5 squared here, and this is giving an answer of 29 over 600. We then have the random variable y defined to be 30 over x, and I need to find the expectation of y and the variance of y. So the expectation of y is simply the expectation of 30 over x. Well, the constant of 30 can come out. It's 30 times the expectation of 1 over x, and that's the answer we obtained in part A. So we're looking at 30 times 2 over 5, which gives an answer of 12. For the variance of y, I will follow a similar approach. So the variance of y is the variance of 30 over x. Now we know that the variance is a squared quantity. The 30 will come out squared. So we're looking at 30 squared times the variance of 1 over x. We have the variance of 1 over x from part B. So we're looking at 900 times 29 over 600, which gives an answer of 43.5. And in part D, we need to find the probability of x being less than 3, given that y is less than 20. So we've got conditional probability here. Let's start by recalling that x can take the values of 1, 2, 3, and 4. And we've got this new random variable y to be defined as 30 over x. So y can take the values of 30, 15, 10, or 7.5. We've got the probability of each outcome appearing. This is given here in the last row. And we know for sure that y is less than 20, so it could be 15, it could be 10, or 7.5. And we are asking what's the probability that x was less than 3. Well, x less than 3 is only this case here, where x is 2 and y is 15. So we're looking for the probability of x being less than 3, given that y is less than 20. in the numerator, we've got exactly what we want to have happen, which is the 1/5 here. Whereas in the denominator, we will be having what we know for sure to have happened, which is the y being less than 20, which is 1/5 plus 3/10 plus 2/5. If you plug this on the calculator, you get an answer of 2/9. In question 5, the weights x grams of a particular variety of fruit are normally distributed with mean 210 and variance 25 squared. We've got the fruit selected at random, and we need to show that the probability that the weight is less than 240 grams is 0.8849. So we're looking at the probability of x being less than 240. I'll be using standardization, so it's the probability of z being less than 240. We deduct the mean of 210, we divide by the standard deviation of 25. So we're looking at the probability of z being less than 1.2. So if we go to the table of values, for 1.2 we read of the value of 0.8849, and therefore the probability we were asked to find is 0.8849 as required. In part B, we need to find the probability that the weight of this fruit is between 190 grams and 240 grams. So I will start by drawing my bell-shaped curve. We want to be between 190 and 240. So this is the probability of 190 being less than x being less than 240, which I will split as the probability of x being less than 240 minus the probability of x being less than 190. Well, from part A, we know that the probability of x being less than 240 is 0.8849. And for the probability of x being less than 190, I will use standardization once more. So we're looking at the probability of z being less than 190 minus the 210 over the standard deviation of 25, which leads to 0.8849 minus the probability of z being less than negative 0.8. We know that for us to use the table of values for the normal distribution, we need to have a positive value here. So I will apply two changes. So we've got 0.8849 minus 1 minus the probability of z being less than 0.8. So the first change is the negative becoming a positive, and the second change is the probability becoming 1 minus the probability. So we've got 0.8849 minus 1 plus the probability of z being less than 0.8. And going to the table of values here, for 0.8, we read of the value of 0.7881. So we're looking at 0.8849 minus 1 plus 0.7881, which gives an answer of 0.6730. In part C, we need to find the value of k such that the probability that x is between 210 minus k and 210 plus k turns out to be 0.95. So once more, I will draw my bell-shaped curve. We can see that the interval is symmetric about the mean of 210. All of this probability is 0.95, so the remaining 5% will be split evenly in the two tails. So each tail will be 2.5%. So all of this can be summarized into the probability of x being greater than 210 plus k being equal to 0.025. I know that this probability can be found in the small table of values. I've got the right direction here, so I will standardize to get the probability of z greater than 210 plus k minus 210 divided by the standard deviation of 25 being equal to 0.025, which leads to the probability of z being greater than k over 25 being equal to 0.025. And going off to the small table of values, we can see that the probability of 0.025 corresponds to z being 1.9600. And therefore k over 25 is equal to 1.9600. And if we cross multiply, we get that k is equal to 49. We now have a wholesaler who's buying large numbers of these fruit, classifying the lightest 15% as small, and we need to find the maximum weight of a fruit that is classified as small. So on a bell-shaped curve, we're trying to find that value x such that the probability of being less than x is 0.15. So this is what we're trying to solve here. The probability of x being less than or equal to small x is 0.15. I will start by standardizing, so the probability of z less than x minus 210 over 25 is equal to 0.15. Well, the 0.15 is a value we expect to find in the small table of values. To be compatible with that table, with the small table, we need to have a greater than direction in the inequality here. So I will apply two changes. It's the probability of z greater than 210 minus x over 25 being equal to 0.15. And if I go to the small table of values for 0.15, the corresponding z-score is 1.0364, which means that 210 minus x over 25 is equal to 1.0364. I will cross multiply to get 210 minus x is equal to 25.91, and therefore the value of x is 184.09. Finally, in part E, we've got the weight y grams of a second variety of this fruit following a normal distribution with mean mu and variance sigma squared. We are told that 5% weigh less than 152 grams and 40% weigh more than 180 grams, and we need to determine mu and sigma. So the first piece of information is that the probability of y being less than 152 is equal to 0.05. I will standardize, so we're looking at the probability of z less than 152 minus mu over sigma being equal to 0.05. Again, the 0.05 probability appears in the small table, so I need the inequality direction to be greater than. So we're looking at the probability of z greater than mu minus 152 over sigma being equal to 0.05. So going to the small table, the corresponding z-score is 1.6449. which means that mu minus 152 over sigma is equal to 1.6449, and therefore we've got that mu minus 152 is equal to 1.6449 sigma, which means that mu is equal to 152 plus 1.6449 sigma. Now we will follow a similar approach with the second piece of information. We've got the probability of y greater than 180 being 0.4. I will standardize the probability of z greater than 180 minus mu over sigma is equal to 0.4. So from the small table of values, we see that the corresponding z-score is 0.2533, which means that 180 minus mu over sigma is equal to 0.2533. I will cross multiply to get 180 minus mu is equal to 0.2533 sigma, and therefore 180 minus 0.2533 sigma is the value of mu. I will combine my simultaneous equations together to eliminate mu. So we're looking at 152 plus 1.6449 sigma being equal to 180 minus 0.2533 sigma. I will collect the sigmas on the left-hand side, which gives me 1.8982 sigma. And on the right-hand side, I've got the 180 minus the 152, which is 28. Now I will divide both sides by 1.8982, which gives sigma to be 14.7508 ... which correct to three significant figures is 14.8. And I will proceed in finding mu. We know that mu is 152 plus 1.6449 times sigma, which is 14.7508 ... I'm using full accuracy here. This gives an answer of 176.2636 ... which correct to three significant figures is 176. In question 6, we've got the variables x and y with the following regression equations based on a sample of 12 observations. So we've got the regression of y on x and then the regression of x on y. We need to find the point of intersection of these lines and then show that sigma x is 25. Well, the first part, it's obvious. I need to solve the simultaneous equations here. So I will substitute one into the other. So we're looking at y is 1.4 and I will replace x with 1.2 plus 0.2y, close the brackets, plus 1.5. I will expand to get y is equal to 1.68 plus a 0.28y plus 1.5. Now I will collect the y's on the left hand side to get 0.72y being equal to 3.18, and if I divide both sides by 0.72 I get that y is 53 over 12. I will then proceed to find x. X is 1.2 plus 0.2y and y is 53 over 12. So if we plug this on the calculator we get an answer of 25 over 12, and therefore we conclude that the point of intersection has coordinates 25 over 12, 53 over 12. This is the point of intersection of the two lines. Now for the second part, to show that sigma x is 25, I will start by writing out the two straight lines. We know that x bar, y bar is always a point on the regression line, so we can say that y bar is 1.4 x bar plus 1.5 and x bar is 1.2 plus 0.2 y bar. So obviously the point we just found here is the point of intersection between the two lines. It's x bar comma y bar. So since x bar is equal to 25 over 12 and we know that x bar is the sum of the x values over the number of values, which we know we had 12 observations, then we can safely conclude that sigma x is 25 as required. We are additionally told that sigma xy is 6961 over 16. We need to determine the value of sxy. Well, I will repeat what I did in the previous part now with y bar. So y bar must be 53 over 12, which is equal to sigma y over 12, and therefore we conclude that the sum of the y values is 53. Well, let's recall that sxy is the sigma xy minus the sigma x times the sigma y over n. We know the sigma xy, we've got the sigma y. We have just found in the previous part that sigma x is 25 and we've got 12 observations. So sxy will be the 6961 over 60 minus 25 times 53 over 12, and if we plug this on the calculator we get an answer of 5.6. Now for the last part, part C, we need to find the product moment correlation coefficient between x and y. Well, let's recall that the product moment correlation coefficient R is given by sxy over the root of sxx times syy. Well, the first line of best fit was y is equal to 1.4x plus 1.5. We know that the gradient of 1.4 was found by doing sxy over sxx, and the second equation we had was x is 1.2 plus 0.2y. So this time the gradient of 0.2 is the sxy over the syy. So I will take the expression for the r for the PMCC and I will square everything. So r squared is equal to s squared xy over sxx times syy, which can be thought as sxy over sxx times sxy over syy. Well, this sxy over sxx is simply the 1.4, and the second term is the 0.2. So we're looking at 1.4 times the 0.2, which gives an answer of 0.28, and therefore r is simply the square root of 0.28, which gives an answer of 0.529, correct to three significant figures.